Good morning. Today we're going to talk about more probability. So, one of the great questions to ask would be, what would be the probability of snow in April in Utah, in Salt Lake City? Forget the rest of Utah. And that one, I'm not enough of a weatherman to find out. If I said what was the probability of snow in December 2020 in Utah, well, that's past. We know there's no probability. It was zero this year. Um, yeah, it didn't help. It was 70 the last few days. Indeed, it was. But yeah, it's snowing today. At least at my house, it's snowing. So maybe at yours, it's only raining, depending on where you live, but it's snowing here. So, okay. Are there any questions about last lecture? Okay, well, we're going to review some of it anyway. Here's a reminder, your homework is due Friday night, 11:59 p.m. Okay, don't forget. So today we're going to continue talking about probability. In particular, we're talking about conditional probability Bernoulli trials, and that's really fun stuff. It happens all the time. So let's ask the question. Let's remind you, okay, that when we're talking about probability, we're talking about experiments. And experiments have a sample space, namely, what are all the possible outcomes of the experiments? Okay. And we assume the likelihood of any particular experiment is known. I'm sorry, of the possible outcomes is known. So up to now, and for at least part of today, we're assuming that the events have equally likely outcomes. But that's not necessarily the case. And we're going to go into cases today where it's not true. Okay, the next thing is if a single event is equally likely, like tossing a coin, sometimes experiments consist of multiple single events, and those can lead to not equally likely outcomes. So we're going to look at that case today. So here's an example. If you roll two dice and the outcomes, you look at the outcomes as the sum of the two, we already had the fact that not all outcomes are equally likely. So if you talk about one die being red and one being green, then you have the possibility of looking at them as ordered pair, and then you can make them equally likely. Okay? All right. So remember the probability. Everything in chapter 5 is totally relevant here in chapter 6, because in chapter 5, we ask the question of how many of something are possible in the cases. Like we asked if we were creating a bag of fruit and we wanted to take 4 kinds of fruit and we were buying 15 kinds of 15 items, 15 altogether, how many different possibilities are there? So that's how many. Now, when we ask probability, what we're asking for is, given we're asking for something that we call an event, which is a subset of possible outcomes, then we're saying how many are possible with that outcome divided by the total number of possible events, and that's the probability. Now, sometimes we use the rule of complements. What's the rule of complements? Yes, the rule of complements is that sometimes it's easier to count unsuccessful outcomes. Okay? So if I ask you how many outcomes have at least one of something, it's easier for me to tell you because then it could be 1 or 2 or 3 or however many. So it's easier for me to figure out the total possible outcomes and, and subtract off the ones that don't have any, because then the rest have at least one possible. Okay, so the rule of complements when applied to possibilities is that the probability of an event E, remember an event is a subset of possible outcomes. So the probability of event E is equal plus the probability of its complement, the probability of it not happening equals 1. Remember, 1 is the biggest probability there can be. That means it's totally happening. Okay. To remind you of a few more things, we have two events are disjoint or mutually exclusive if they cannot occur simultaneously. They're said to be independent if the occurrence of one event does not influence or be influenced by the occurrences or not occurrences of another event. So the rule of sums, the two different rule of sums occur when you're looking at possibly disjoint events. So a sum of rules for disjoint events says that if they are disjoint, then the probability of E1 or E2, remember we're looking at or here, or. So the probability of E1 or E2 is the probability of E1 plus the probability of E2. Now we're going to jump using using some set theory. Remember last time I said I didn't want you to, but now we're experienced folks. So you can say E1 union E2, that's or, remember. Or is like union. And the general sum rule, if you think back, if events are not disjoint, then if E1 or E2 are events, then the probability of E1 or E2 is the probability of E1 plus the probability of E2 minus the probability of E1 and E2. And that falls right out of the inclusion-exclusion rule. Remember, the inclusion-exclusion rule says if I have two sets, then the number of elements, remember, probability looks at the number of elements in the events consisting of E1 or E2 is equal to the number of events in E1, the number of events in E2, minus the number of events in their intersection, because we've counted that twice, all divided by the number of possible events. Okay. Yes, you can use the cup notation when we're looking at two elements from now on. Okay, and you can use intersection for and. So we also have an independent product rule that says if two events are independent, then the probability of both occurring, that's E1 and E2 occurring, is their product. Okay, their product. Okay. Let's look at some examples. Okay, so we have a card is drawn from an ordinary deck of 52 cards. What's the probability that the card is a diamond, a club, or a king? Okay. Now this is an interesting problem because we can solve it two ways. Let's take the easier way first, okay? Let's let E1, we didn't do this one last time, be the event that the card is a diamond or a club. Card is a diamond or a club, that's E1. And E2 is the probability that it's a king. Okay, we have E1 and E2. Now, when I say it's a diamond or a club, how many elements are in E1? How many possible outcomes can there be if I say what's the number of outcomes that are in E1? Well, it's 26. Diamonds are 13, clubs are 13, They have nothing in common. Okay. What's the number of events in E2?
4.
4. Okay. What's the number of events in E1 and, remember the intersection, and E2?
2.
2. That's right. There's one king that's a diamond and one king that's a club. Okay. So what are our rules for probability? Well, the probability of E1 is equal to a half. 26 over 52 outcomes possible. The probability of E2 is 4 over 52, or 1/13. The probability of E1 and E2 is equal to 2 over 52, or 1/26. Okay, so the general sum rule says the probability of E1 or E2 is equal to the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Okay, and if we put those all over 26, we get 13 over 26 plus 2 over 26 minus 1 over 26 is 14 over 26, which equals 7 over 13. Okay? So it's very powerful.
Professor, question for you.
Yeah.
You have an occasional volume pop-up that shows up and it obscures part of your screen. Is there a way you can disable that?
I think I've got it. I'm sorry, I took care of that. The problem is that in order to show my iPad, I'm using QuickTime and I can't get rid of the thing that allows me to stop or record. So I'm just getting it out of the way now, so it shouldn't be there. I'm sorry. Okay? We caught it early.
Yeah, thank you.
Okay. So is this clear? So let's move on.
Wait, maybe one question.
Yes.
So if I understand the rule of sums right, when it's and, you add them together, and then when it's or, you add them together and subtract the...
No. When it's and, we don't add them together. Look here. Probability of E1 and E2 is the probability of E1 times the probability of E2 if they're separate events.
Times.
If they're separate events. If they're, independent events. These are not independent events. We'll get to more general and in a little bit, okay?
Yeah, okay.
Good. We just want to practice a few cases here before we get there. Okay. So let's talk about independent events again. Okay. So if you roll a 6-sided die 4 times, I think we did this last class, didn't we? Maybe. If we roll a 6, I'm sorry?
I don't remember if we did or not.
Oh, well, we'll do it today. If we roll a 6-sided die 4 times, let E1 be the event that the first 2 rolls sum to 7, and E2 be the event that the last 2 rolls sum to 10. Are they independent? Does the result of the first 2 rolls affect the occurrence or non-occurrence of the last 2 rolls? No, it doesn't. They're independent. Now, if I asked you if the sum of the first two rolls affected the sum of the second and third roll, would that be independent? No, because the value that you have on that second roll occurs in two different problems, and the result of the number of possibilities affects it. So that wouldn't be. But this case is independent. Okay, what's the second one? Second one is you have an even number, a jar with an even number of red and white marbles. Suppose you pick one, note its color, and put it back in the jar. That's called picking with replacement. You do that 4 times. So it is the case that the probability of any one pick is not affected by the other. But if we ask the question, E1 is the event that the first pick is red, and E2 is the event that at least half the picks are white. Do they affect each other?
Yes.
Yes, absolutely. Not independent. We're going to come back to this and look at it again. And we're going to come back to this third one too. Okay. So why are they not independent? Because if the first one is red, okay, then 2 out of the 3 next picks have to be white in order to get at least half. 2 out of the 3 or 3 out of the 3. Whereas the first pick is not red, if it's white, then you only need 1 out of the next 3 to get at least half. Okay? So the probability differs depending upon the result of the first pick. Okay. When choosing a committee of 3 people from a club with 8 men and 12 women, let E1 be the event that the committee has a woman, and E2 be the event that the committee has a man. Now, if I think of each one separately, they don't affect each other. But if I change that to say that the first pick is a woman, then it changes the probability of whether a man could be one of the next 2 picks. Okay? Not independent is equivalent to dependent. Yes. Okay? Absolutely. Sorry for not being clear about that. Okay, good. So this one is dependent. Okay. That, let's say the committee first, oops, sorry. Wow. Well, that was weird. Okay, so let's go on. Let's look at the independent product rule. So obviously we're going to come up with one that isn't, but let's look at this first. What's the probability of rolling a fair 6-sided die 6 times and having only odd numbers result? What's our sample space to pick from? Okay, so let's first ask what the sample space is. So let's ask the sample space. Well, we're rolling a fair die 3 times. So what are our possibilities?
It's 6 times.
We have heads, or I'm sorry, we have 6 possibilities here, 6 here, and 6 here. So
There's
that's
6 times. So that's 6 times 6 possibilities.
So what, I'm sorry, I don't understand. We have 6 times 6 times 6, right?
Yeah, the
Yes,
yes, we're
probability of
rolling
a
the
Number
fair
of
dice
die.
six
elements in the sample space is 6 cubed.
It's 6 to the 6th. You're rolling the 6-sided die 6 times according to the problem.
6 times, wow. Thank you. Good. Whew, we'll get it right now. Good. Okay. Now, what's the probability of having only odd numbers result? So what's the probability of getting an odd number in the first slot?
So there have three odd numbers, so there's 50%, one or two.
Yeah, so the probability, let's say of EI, that's the probability of rolling an odd number on the ith roll is equal to a half. Right? So E is the event of rolling a fair die having only 6 times, having only odd numbers result. So that's equal to E1 and E2 and E6. Has to happen all 6 times. Notice in this case, E is kind of like a composite event. Okay, so there is no answer if I just look at E1 because that's only one roll, and there is no answer if I look at E2, that's only one roll. So I have to look at all 6 rolls. Okay, so my experiment says I'm looking at 6 rolls. Okay, so E is having and. Now, are the E sub I independent? Does the ith roll affect the result of the jth roll?
They're
No.
independent.
I'm sorry, what?
I just said independent.
Yes, very good. The roll are not affected. So in that case, our rule says that the probability of E is equal to the probability of E1 times the probability of E2 times the probability of E6, which is equal to 1/2 to the 6th. Okay. So here we have a case that the probability of each roll is 1/2, but the probability of the event, that's the composite of all of them, is definitely not equal in the space of all possible rolls, because you have 6 to the 6th of them equally likely. Okay, very good. Okay, so let's look at this problem. And we're going to look at 2 parts of it. So here we're looking at rolling a 6-sided die 4 times. I got confused, notice. Last time I thought it was wrong. So here, what's our sample space if we roll it 6 times? The number of events in our sample space, N of S, is equal to, you have a 6-sided die, so each side is equally likely. And we're rolling it 4 times. So we have 6 to the 4th possible outcomes. Okay. E1 is the first 2 rolls sum to 7. So how many events are in E1? How many ways can we sum to 7? Well, we can do 6 and 1, 5 and 2, 4 and 3, 3 and 4. Um, 2 and 5, and 1 and 6. Remember, here order matters. We're keeping track of the order that it was rolled. So how many do we have here? We have 1, 2, 3, 4, 5, 6. So we have n of e is 6, E1. What is n of E2? N of E2 is the event that the last two rolls sum to 10. Okay, how many ways can we get 10? We can get 6 and 4, we can get 5 and 5, and we can get 4 and 6. So we can sum to 10 3 different ways. Okay, so are these events independent? Yes, Jordan.
There be 2, 5, and 5 since we have 2 independent dice.
We do have 2 independent dice, but a 5 and a 5 are they're the same rolls.
Yeah, so like if we had a green die and a blue die,
Yeah.
would it be the same if the green die was 5 and the blue die was 5? And then if, well, I guess I just answered my question. Never mind.
Great. Good job. You did it yourself. Okay. So they're independent. Now, so we look at that and say, well, then since they're independent, the probability of E1 and E2, okay, is equal to the probability of E1 times the probability of E2, which is equal to 6 over 6 to the 4th times 3 over, no, that's 6 squared. We're only rolling it twice. Sorry. So we're looking at the whole space, but remember, these are only partial probabilities. So this is 6 over 6 squared, and this is 6 over 6 squared, because we're only looking at grouping the first two and the second two. So the first two have 36 possibilities, and the second two have 36 possibilities. So in that case, we have 18 over 6 to the 4th, or 3 over 6 cubed. And we could do more on that, but I'm leaving it there. Okay. All right. Now, suppose we go, yes, Isaac, or Isaac first, then Dane. Yes. Isaac? I can't hear you if you are asking something. Well, let's try Dane.
I had a
Now Isaac,
so-
you're there, Isaac? Let's try Dane. What's your question, Dane?
my question was on computing the probability of E1 and E2.
Yeah.
So alternatively, could we make use of the generalized sum rule,
No.
but solve for it?
That's a very good question. Okay. Because when we're looking at this problem, the generalized sum rule says we're looking at a subspace. Each of our pieces takes the whole problem and looks at a subspace of that. So then we're looking at some subspace of all possible events. But in this case, we're looking at a subspace of, if I look at it this way, we can look at it differently. But if we're looking at this, we can look at it as the subspace of just the first two. Now, if I want to look at it that way, I can do that. But then the number of events changes. The number of events in, let's call it E1 twiddle, is 6 squared. But then we're looking at all possible events for the second two. I'm sorry, it was 6, not 6 squared. What am I doing?
That makes sense because we're not working on actual subspace in this problem right now. We're working on like, I mean, it's not even a subspace, but yeah, I understand now. We
Exactly
didn't have the right
right.
probabilities.
Exactly right. If we want to think of it as a subspace, then we're looking at 6, and then the number of events is 6 times 6 squared for the last two. And the number of events in E2 twiddle would be 6 squared times 3 events. Okay. Okay, so then you're looking at events as sub, but you're still saying and. When you say and, not or, then you multiply.
That makes sense. Thank you.
Isaac, yes, you have a question now?
Yeah, sorry, can you hear me now?
Yes, I can.
Okay, great. My microphone is just a bit broke. So if the problem was slightly different and it said you rolled it 3 times,
Yes.
that would mean they're independent, or that would mean they're dependent, right? Because one number would have to be in both sets.
Yes.
Okay. And that would, for that, when we're solving it, would we mostly be counting the different options, or would there be a better way to go about solving that if they were dependent?
Well, we're going to deal with dependent in a moment. Okay.
Okay, sounds good.
Let's finish the second half of 4, and then we're going to roll into what happens. Okay. So here's problem 4, the second half. It's our jar with red and white marbles. Okay. So E1 is the event that the first pick is red. E2 is the event that at least half the picks are white. So let's look at that again. So if E1 is a pick that the first pick is red, okay, then we're looking at the probability of E1. It's the first pick, and that's a half. We're not looking, remember here, we're not looking at all of the picks. We're only looking at the first one. So it's either red or white, and it's equal probability because they're equal numbers of marbles. Okay, now the probability that at least half of the picks are white, probability of E2. Okay, so here we're looking at the probability that exactly half the picks are white. Plus the probability that 3/4 of the picks are white, plus the probability that all 4 picks are white. Notice we're adding this. Why are we adding this? Because they're in disjoint events. So when we say at least half, that means 2 of the picks are white, 3 of the picks are white, 4 of the picks are white. Okay. So what would that be? Well, half the picks are white would be a half. The probability that 3 of the picks are white, it's the number of combinations of 4 things taken 3 at a time over what are the picks? 4. No, 2 to the 4th. Plus the number of 4 at a time. And that whole thing, if I do it right, if I do my arithmetic right, adds up to 4/16 or 1/4. Nope, wrong way. wrong computation, is 11 over 16. Okay, now let's figure out the hard way. What's the probability of E1 and E2? Okay, so we know we're always going to divide by 16 because we're picking 4 times and it's 2 to the 4th. That's our total sample space. Okay, now E1 and E2, let's see, if it's E1, this is red. Okay, now how many ways can I get the next 2 out of 3 to be white? Well, that's C of 3, 2. I got 3 picks, 2 of them have to be white, or C of 3, 3. So C of 3, 2 is 3. C of 3, 3 is 1. Are there any other choices? No. So I have a total of 4 possible ways over 16. So that's probability 1/4 of having the first one red and at least 2 of the total white. What is probability of E1 times the probability of E2? Well, that would be 11/16 times a half would be 11/32, if I got this right. Now, that's not equal to 1/4. So obviously, the product rule doesn't work for this case, and it doesn't work for this case because they're dependent events. They're not independent events. Okay, so let's learn some more things, okay? 2 events, remember, independent if the occurrence of one doesn't affect the other. Now we're defining conditional probability. Given events E1 and E2, like picking our marbles, we denote the probability of E1 given E2. In our case, we'd say the probability of at least half the marbles being white if the first marble is red. Is the probability that E1 happens given that E2 occurs. If E1 and E2 are independent, then we have the simple product rule. If they're not, then we're going to have a different rule. Yes, U1099080.
When it says the general product rule, does that mean the dependent product rule where there's 2 dependent things?
Well, it turns out that the general product rule works whether they're independent or dependent.
What's that?
Okay, because the general product rule says if E1 and E2 are any events in a given experiment, then the probability that both E1 and E2 occur, that's E1 and E2, is the probability of E2 times the probability of E1 given E2, which is also equal to the probability of E1 given times, the probability of E2 given E1 occurred. Now, if they're independent, then the probability of E2 given E1 is just the probability of E2.
So it's like the general product rule you could use for anything, and then you could use the independent product rule because it's easier.
I'm sorry, say that again.
Is it like you could use the general product rule for anything, and then you could use the independent product rule because it's easier?
Yes. Basically, it's the same kind of thing. Just think about the sum rule, okay? If the events are disjoint, then there is nothing in the intersection. So the and is empty. So you're subtracting off nothing. In this case, if they're independent, then the conditional probability is the same as the probability because it's not affected by whether the other one occurred. Okay,
Okay.
good. Let's keep going. Let's do some conditional probability and try and figure out how to do that. Oops, we'll do that right after the break. Here's a break. Ask any questions you want.
I have a quick question about the general product
Yes.
rule. So it says that it's equal to probability of E2 times probability of E1 bar E2. Is that
Given E2, that's the way that's read.
okay? Given E2, okay.
If you say bar, I think of the line over the top, and that's not the right one, okay?
Okay.
So when you see that, in this case, sometimes that bar means divides, but not in probability. In probability, it means E1 given E2.
So that kind of means that we assume that E2 is already in effect.
Yes, when the problem is stated, that's how it's stated usually.
Okay.
Or note that if E2 is given, so it all depends how you phrase it. This is kind of cool stuff, mind you. Okay.
So in the previous problem, would like say E1 given E2, would that be like picking the probability of picking a red marble given that you've already picked a white marble or something like that? Maybe it was switched, but something like that.
E2 given E1, what's the probability of picking at least half white marbles given the first marble was red? Absolutely.
Okay, thanks.
Very good. Any other questions?
What does that mean for the probability? If something is given, does that mean you like add it along with the probability of E2?
We're going to talk about that shortly, okay? That can be confusing, but notice what you're doing here in this rule is you're saying the probability of both occurring is the probability of, let's say here, probability of E2 times the probability of E1 given E2, okay? So it's a more general kind of product rule. Remember, in this case, when we're doing multiplication, E1 and E2 are not whole answers, okay? They're pieces of an answer. So when we talk about outcomes, say in the case of picking marbles, okay, what we were talking about is E1 was an individual pick of marbles with, that's not a whole answer. And E2 is at least half. So that could be a whole answer, but then you're saying, well, it all depends on what happens on E1. Okay, so you can figure it out separately like we did, or you can use this product rule, which makes life a lot easier for more complex cases. Remember back here, what we did somewhere here, what we did is we counted. We said, how many ways can I do it? Okay, so using the general product rule is generally easier once you understand conditional probability. Okay, so we're going to work on understanding conditional probability right now in about 2 more minutes.
So, Professor, I remember some equivalence that probability of A given B was equal to, I think it was A and B over B. Is that the right equation? And is that for?
Look what we have here. Let's go back here. look what we have here. We have the probability of E1 and E2. Let's say I can do divided by the probability of E2 is equal to the probability of E1 given E2. All I did was take this first equality and divide both sides by E2. Or you can look at the first and the third line and divide by E1. Does that help?
Yeah, so
Yeah.
that's for a general case then.
Yes, absolutely. Okay.
All right, thanks.
Okay. I think we're on now. Good. So let's consider the differences in the statements of when you're choosing a committee of 3 people from a club of 8 men and 12 women. E1 event be the event that it has a woman. E2 be the event that it has a man. What's the probability of E1? Well, the probability of E1 that it has a woman is 1 minus the probability that it has no women. Because when you say it has a woman, it could have 2 women or 3 women. That's the at least one. So what we look at this and say, well, what are the set of all possible committees? Well, that's the number of combinations of 20 choosing 3. Because we're taking all people, taking all subsets of 3. Okay, notice there are no repeats. They all may be men, but they're different men, different women. So the number of events in E1 is the number of events in the sample space minus the number of events with number of committees with no women, which is no women is all men. So that's the number of combinations of 8 things taken 3 at a time. So the probability of E1, it turns out to be 0.95088 carried out to that many places. Similarly, the number of committees that are all women and no men, which we're holding on to this for later, is the number of combinations of 12 choose 3. So the probability of E2 is equal to 1 minus the number of events in E2 complement divided by the number of events in the sample space, which is 1 minus 12 choose 3 over 20 choose 3, which is 0.8070. Okay. Lower probability we're going to get a man, huh? So when choosing a committee of 3 people, what's the probability that the committee has a woman on it, given that it has a man? So let's assume that the man was chosen first, since order doesn't matter here. Let's assume it's chosen first. So now we're asking, what is the probability that it has a woman, given that it has a man? Okay, you notice the given part. So that tells you it's E1 given E2. So we have to figure out a few things that way, okay? So let S2 be the possible committees of 3 that have at least 1 man. Do we know how many people are on that? At least 1 man. Well, it's the number of people. Yes. No question. I thought I saw a hand up here a second. Okay. Good. At least 1 man. Now the number of committees in E2 column. What's E2 bar? E2 complement is the number of committees that don't have any men. And that's 12 choose 3, the committees that are all women. So the number of elements in S2 is equal to the number of elements in S minus the number of elements in E2, which is 920. At least one man. Okay. So the possible committees for E1 given E2. So we have to have one man and two women, or two men and one woman. Is there any other possibility? No. So the number of committees with one man and two women, well, the one man could be chosen 8 different ways. And then two women is combinations of 12. It's 12 choose 2. Two men and one woman is 8 choose 2 times, well, 12 choose 1 or 12. So the probability of a woman on the committee given a man on the committee is 8 times 12 choose 2 plus 8 choose 2 times 12 divided by 920, or 0.9391. Okay, notice our sample space in this case is not the original whole sample space. The sample space changes because we're assuming that we're given that there's one man, at least one man on the committee. Yes, Grant.
What about the case where it was 3 men? Wouldn't that not be possible since there's no room to add a woman to that committee?
Yes, I don't have that case.
But for S2, wouldn't S2 include that case?
S2, let's look, what is E2? E2 is, sorry, E2 is the event that the committee has a man. So the complement of E2 says there are no men, which means all women. Okay. So I'm subtracting I'm subtracting the all woman case. Okay. So now I have committees that have 1 man, 2 men, or 3 men.
Right, that's my question. Like in this problem,
That's the 920. That's my sample space. I'm given there's at least 1 man. So there could be all men. There could be 2 men out of 3 people. There could be 1 man and 2 women. Those are my only possibilities.
okay, so it is possible that there are no women in the committee?
That's in those sample space S2.
Okay,
It's not possible. I'm looking at the probability that there's at least 1 woman given that there's a man. Okay. So that's why my probability isn't 1, because I have to exclude the case where it's all men. Okay. Okay. Does it make sense? He's gone. I suppose it does. Okay, good. So let's look at what would happen if we had applied the simple probability rule. Okay, what we would get is the product of E1 times the probability of E1 times the probability of E2, which would have given us 0.7674. Notice that ain't right. When we're looking at the probability of E1 and E2, so that's the probability of E2. What's the probability of E2? What was E2 again? Probability of E2 is the event that the committee has a man. So we're given that the committee has a man. The probability here is the probability that there's a woman, given that there's already a man on the committee, is the product of those two, which is 0.7579. Now you can look at it and say, well, they're kind of close, but not really. They're not the same. Okay. All right. So you can always double check these answers, the and, by going in and saying, what are the possible committees? Okay, 2 men, 1 woman, which is 8 choose 2 times 12 over 20 choose 3. That's the probability of 2 men and 1 woman. And then we have the probability of 1 man and 2 women. And then we add them together because each collection is possible. So we add them together. Those groupings are disjoint. You can't have a committee of 3 with 2 men and 1 woman and 2 women and 1 man. That doesn't work. So we end up with this answer. And if we do the division, we end up with the right thing. Okay, let's do another practice problem. This has 2 parts to it. In blackjack, your opponent receives a face down card and a face up card. I am not a card player. If you're not a card player, then we're in the same boots, but let's just go with what we see here. You can see the face up card. Specify events E1 and E2 so that the given question is about the probability of E2 given E1, and then answer it. What's the probability that excuse me, what's the probability that his face down card is a 10 jack queen or king, given that you see his face up card is an ace? Okay, here we're asked the probability of E2 given E1. E2 given E1. So what are we given? What do we know?
See that there's 1 less card in the deck.
Well, we know his face up card is an ace. So E1 is that his face up card is an ace. Okay. If I see it, I know it. Excuse me. Oh, that's good. Did happen. Good. All right. So what's the probability? What's E2? Face down card is a 10 jack, queen or king. That's E2. So what is the probability of E2 given E1? So what's our sample space, by the way? Our sample space for this problem is what?
The full deck minus the aces.
The full deck minus 1 ace.
Oh, 1 ace.
You only see 1 card. So the number of outcomes is 51. Possible things that he could have. What are the number of events in E2 given E1? 10, jack, queen, or king. So there are 16 of them. So the probability of E2 given E1 is equal to 16 over 51. Okay. Just conditional probability. Okay, now let's look at the second one. What's the probability that his face down card is a 10, Jack, Queen, or King, given, when you hear that word, given that you see his face up card is an ace, and you know that your own hand consists of 2 kings? What is our sample space now? How many elements in the sample space?
49.
49, very good. Okay. And how many elements possible in E2 given E1? Well, what is E2 again? E2 is the same, 10, Jack, Queen, or King, that's E2. But now E1 changes. His face-up card is an ace, and you have your own hand consisting of 2 kings. That's E1. So how many possible ways could he end up with a 10, Jack, Queen, or King?
14. 14 because I have 2 kings, so they only have the 4.
That's right.
14.
Very good. So the probability of E2 given E1 is equal to 14 over 49. Okay? That's called conditional probability. Okay. I want to move on, and I will come back and do, we're going to mark problem 6 and come back. I want to move on and talk about a new idea and then come back to it. And that's at a Bernoulli trial. I don't want to skip this, so I want to give it a few minutes, and then we'll do more practice problems on both cases. Okay? So in a Bernoulli trial, we're looking at every example we've had recently is an experiment that it's based on independent repetition of a simpler experiment, rolling a die, tossing a coin, asking a question, which we're going to do, like, how many ways can you win 3 out of 5 when it's totally independent which ones you win? So when we talk about that, an instance of a simpler experiment is called a trial, more generally a Bernoulli trial. So the outcomes for the larger experiment are not equally likely, even though the simpler, the trial outcomes may be equally likely or not. And Bernoulli has a nice theorem. This is great. Okay. If an event that occurs with probability P, if the trial is repeated independently many times, then the probability of having K successes in the M trials is the number of combinations of M things taken K at a time times the probability of P to the K times 1 minus P to the M minus K. Okay? So remember, if I'm asking how many ways can I win, what's the probability of my winning 1 game out of 3? Okay, I can win the first game, I can win the second game, I can win the third game. But then I can't win the other 2. Okay, so this is a nice theorem, and we're going to use it instantly. So a soccer forward has a probability of 1/3, 0.33, of scoring a goal in a game. What's the probability he'll score it in exactly 1 game out of 4 successive games? Each outcome is goal or no goal. So what is my sample space? My sample space is listed there. There are 16 outcomes. I can have no successes, no goals. I can get 4 goals. Ooh. And I can get 1 goal 4 different ways. I can get 2 goals a bunch of different ways. I can get 3 goals 4 different ways and 4 goals 1 way. So I get all these spaces here. Okay, that's my sample space. The product rule is applied to get the probability for the outcome for one of them. What's the outcome for one of them? They're independent. So it's 1/3 times 2/3 times 2/3 times 2/3, 8 81sts. Okay, I fail 3 times, I get success once. But we're not asked for that probability. We're asked for the probability of goal, no, 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 no goal, no, 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 no goal, no, or no, no, no goal. They're independent, so we add their probabilities. Okay, so we add them together and we get 32 over 81. Okay, notice that that's just an application of the Bernoulli theorem, okay, where this is 1/3, P is 1/3, K is 1, M is 4. So we're looking at 4 choose 1 times 1/3 times 2/3 cubed. And that's indeed the answer we get. How does the problem change if you ask the probability of at least 1 goal out of 4 successful games? At least 1 goal. We'll get to that. Suppose you have a biased coin that comes up heads with a probability of 4/7. So the probability of head equals 4 over 7. What's the probability that in 10, M equals 10 if we're applying Bernoulli? Successive tosses of this, it's not a fake coin, it's a biased coin. We get at least 8 heads. So we at least 8 says we want to ask K equals 8, K equals 9. So it's 8 or 9, or K equals 10. Notice we can't get 8 and 9 and 10. We're getting 8 or 9 or 10. So what's the probability of getting 8? Well, it's 10 choose 8 times 4/7 to the 8 times 3/7 squared. The probability of getting 9 is 10 choose 9, which is 4/7 to the 9 times 3/7 to the first power. And the possibility of getting all 10 is 10 choose 10, 4/7 to the 10th times 3/7 to the 0. And then you see that, or they're disjoint events. We add them together. So the sorry. Wow, that's weird. So the probability is C of 10 choose 8, 4/7 to the 8th times 3/7 squared plus C of 10 choose 9, 4/7 to the 9th, 3/7. plus, what's 10 choose 10? 1. So we don't have to write it again. 4 7 to the 10th. And 3/7 to the 0 is just 1. And that's our answer. And if I were working it out on an exam, I'd have to try and combine them a little bit and do a little bit better than that. Okay? All right. So when you say something of at least, that's an or. Okay. Suppose the Jazz win every game they play with a probability of 3/4. If you don't know who the Jazz are, you don't watch basketball. What is the probability that they would win a best of 7 playoff series where you play until one team wins 4 games by a margin of 4 games to 2, by a margin of 4 games to 3? So what do we have for an answer here? So how many games are they going to play? Well, they can win in 4. I'm just going to put W there. W, W, W. Or they can win in 5. And in this case, they're going to win 3 out of those 4. Or they can win in 6. And in that case, they're going to win 3 out of those 5. I don't know which 3, any 3. Or they can win in 7, where they have to win 3 out of 6. Okay? So if they win in 4, okay, if they win in 4, then if we look at that, they're 4 games, 4 successes, 3/4 to the 4, and 1/4 to the 0, according to Bernoulli's theorem. If they win in 5 games, sorry, if they win in 5 games, here we are, 5 games down here. If they win in 5 games, okay, what we have, or the number of possible ways here, is that's 4 choose 3. So we have to have 4 choose 3. And then we have 1/4 cubed, 1/4 loss. And then we have the first one that they won. That's a 3. This is 3, 3/4. Grant, yes.
Maybe I'm just confused by how the question's phrased, but would it just be the only options would be them winning 4 games out of 6 games or 4 games out of 7 games?
It is, but I want to go through all of the possibilities here. Okay?
So
I'm
is
doing extra work. You're not confused.
okay.
The only 2 that matter for this problem are the last 2 possibilities.
Oh, I see.
The more general case would be, what would the probability be of them winning 4 games out of a best of 7? And we can figure out that too while we're at it.
Okay, I get it.
Okay? So 4 out of 5 then is 4 choose 3 times 3/4 to the 4th times 1/4. Out of 6 is they have to win 3 out of 5 here. So that's 5 choose 3, 3/4 cubed times 1/4 squared times the 3/4 that they won the first game by. The last game, I should say. And then we have, this is 6 choose 3 ways. And we have C of 6, 3, 3/4 cubed, 3/1/4 cubed times 3/4. Okay. Notice that in all the games they win, okay, they're winning 4. So we end up with a 3/4 to the 4th power because they've won 4 games. So what matters is how many ways did they win them? How many games did they lose? So in the case where they won 4 out of 6, our answer is combinations of 5, choose 3, 3/4 to the 4th times 1/4 squared. If they won in 7, then we have 6, choose 3, 3/4 to the 4th, 1/4 cubed. What if we just ask the question, best of 7? That means they could win in 4, or they could win in 5, or they can win in 6, or they can win in 7. How would the problem change? What would we do then? We'd have to add. Remember, we just said or. So we would be adding each of these cases together. So remember, asking if they win in the best of 7, in any 4, 5, 6, or 7, you're saying, what is the probability they win in 4, or the probability they win in 5, or the probability of 6, or the probability of 7? So we're adding them together. Okay? Let's do 10, and then we'll go back and catch some more. Suppose Team A has a 60% chance of winning any given game against Team B. What's the probability that Team A wins the best of 3 series against Team B? Okay, so what's the probability he wins? Well, how many games will they play in a best of 3 series? Well, best of 3, that means they can win, that it can be AA, or they're playing in 3 games and A wins the last game, and he can win the first and lose the second, or lose the first and win the second. Okay, so he has a 60% chance of winning. So if he won in 2 games, it's 22.6 squared plus, now we're playing 3 games. This is what would come out of Bernoulli's theorem, because we're only looking at the unknowns in 2 cases. And then we have the known of 0.6. So our answer would be C of 2, well, that's just a 1, 0.6 squared plus 2, choose 1 is 2 times 0.6 squared times 0.4. And if I add them together carefully, I get 0.6 squared times 1 plus 0.8 is 0.36 times 1.8. Okay? Good. Now let's go back. Oops, we don't have time to go back. We'll do a review problem, and we'll do a couple of practice problems in between 6 and I think 9 or 8, whatever it was, next class. Are there any questions about anything we covered today? Bernoulli trials are fun. They come up all over the place. Okay. And then probabilities sort of fall apart on nights when they're tired and all the rest of it. But in the meantime,
I might have a question.
yes, Tyler.
So Mike, I just have a quick one. It's about so for the Bernoulli trial, P is the probability of success.
Yes.
Then K is the number of times we actually succeed.
Yes.
Then M is the number of repetitions.
Yes.
Okay, good.
Got it. Yes, Grant.
Yeah, I kind of have a follow-up question. In the examples that we just did, for the number of successes, would that just be the number of wins?
Yes.
So
We define success here as how can they win? Okay. So do they win? The probability of win. But the event, so an outcome is a win or a loss, but an event here would be winning in 2 or winning in 3 out of 3 kind of thing. Okay.
right, so for the example where they had to win 4 out of 7, I'm confused on why it would be, or I think you did choose 6,3.
Yes. So when they win 4 out of 7, it won't go to 7 games. If they won in 6 games, they'd never play the 7th game. So the last one has to be Team Jazz winning. They have to be in the last spot. So when we're looking at choose, we're saying how many ways can you pick 3 subsets out of 6? Well, I have 6 spots here that I need to fill in with 3 wins for the Jazz. Okay.
And that's
6 choose 3. Yeah. 6.
so K in this problem is actually 3 and not 4.
K in that problem, yeah, that's a little confusing. K, the unknowns in that problem, yes, it's 3, but the probability, you have to throw in the fact that the probability of winning the 7th game was only 3/4 also. So if I ask you what's the probability of winning 3 out of the first 6 games, given that they won the first game, that's what this stuff is. But then you have to remember, multiply if they win 3 out of the first 6 and the 7th game, you multiply by the 7th game. Does that make sense?
Not really. I mean,
Well,
I'll
remember we had a product rule. Here, I'm going to give you an event E1 that says Jazz win game 7. And I'm going to give you an E2 that Jazz win 3 out of first 6 games. Okay. Now, if you remember the probability of E1 and E2, what is that? The probability they win 3 out of the first 6 and they win the 7th game is equal to the probability of E1, they win the 7th game, times the probability of E2, that they win 3 out of the first 6. So in that case, this is the probability that they win 3 out of the first 6. And this is the 7th. So We want the probability that they win 4 out of 7.
Okay. So is that, I see how they're the same. So would it be wrong to assume that K is 4 and that M is 7?
You'd get the wrong answer because you'd have 7 here and 4 there, and that's not the same as 3, 6, 3. 6 choose 3.
Okay.
This part would come out right, but the number of ways that you could get it would be wrong.
Okay.
Okay. So if I tell you, suppose I gave you a different problem. Suppose I said they're going to play 7 games, not a best of 7, but they're playing 7 games. What's the probability that the Jazz win 4 of them? That's the problem you would be solving if you put the number of combinations of 7 things taken 4 at a time times the probability of a win to the 4th times the loss to the 3rd.
All right. Thanks.
Okay. But this is a different statement when we're in the best of 7. Okay. Think about what the differences are. All right. We're done for the day. I'll